All right, I'd like to talk about active and passive earth pressures. We talked about the at-rest earth pressure, and we had the K naught, the earth pressure, at-rest earth pressure coefficient, K naught. And we said for sand it was about 0.4. So I'll go back here. We said sands, K naught, approximately 0.4, for instance. And let's review the definition of K. So, what is it? It's sigma h prime over sigma v prime. And we have, as we mentioned, we have a K naught, we have a Ka, we have a Kp. Ka stands for active, or the A in Ka stands for active, the P in Kp stands for passive. And K naught again is at rest. Those are the three. And we mentioned last time that when we had K naught, there was no movement of our wall. If you remember, that what we did was we had this bucket of sand, for instance, and the bucket was rigid. The walls were completely rigid. They did not move, and that gave us the K naught. All right, I'm going to describe then the active and passive situations, and I like to use bookends as the model because you've all moved into a place and you put books up and you put in a bookend. So the analogy here is that the books that we're holding up is like our soil, and the bookend is like a retaining wall that we're going to build or have. So you got a new bookshelf. You put in your books on your bookshelf, and you take your bookend and you push it up against your books so that they look nice and neat, and then you let go of the bookend, and what happens? Well, when you let go of the bookend what? It moves out just a little bit. And then these books are not quite vertical anymore. They're just a little bit crooked. So what do? You push the bookend again up against the books. They're nice and straight. You let go, and the bookend moves out a little bit again. They're no longer quite perfect, but at that point you just say, okay, I'm just going to have to accept it, because no matter what you do, as soon as you let go of the bookend, it moves a little bit outward and away from the books. It moves in that direction, and you just live with it because the books are good enough. They're almost perfectly straight, but not quite, and it's just acceptable. But you can't, basically there is some movement of your bookend, which is your wall. Now, envision this situation where during that whole process, I put some pressure transducers in my bookend here, and I want to measure the pressure on the face of this bookend during the whole process. So the process is we put the bookend in and we push the bookend toward the books. Well, what happens to the pressure here measured in those transducers? It's going to go up. The pressure is going to go up. Okay, so I measure that, but then what happens when I let go of the bookend and then the bookend moves in this direction? When it moves in that direction, then what happens to the pressure in my pressure transducers? It goes down, the pressure goes down. So what I see is that when the bookend is moving toward the books, the pressure goes up. When the bookend is moving away from the books, the pressure goes down. And that sort of gives me some information about how a retaining wall would behave. And what we use for this is that the Ka, the active condition, is or the active stress condition, and we use Ka for it. That is the situation where the bookend moves away from the books. That is the active stress. And it gives us a lower stress. On the other hand, the passive situation is the bookend is pushed toward the books, is the passive stress, and it's a high stress. So the Kp is going to represent the passive stress where the bookend is moving toward the book. So Kp is higher than Ka because the passive stresses are higher than the active stresses. And okay, so that's the first thing I want you to note. And it's the same thing when we have a wall. You know, if this represents a retaining wall that we've built, and this is our soil, when the wall moves toward the soil, we are getting the passive situation. When the wall is moving away from the soil, then we are getting the active situation. So, all right, let's make some other comments about the wall itself. The first thing is that the wall itself, or this bookend rather, let's talk about the bookend. The bookend is not made out of styrofoam. You've all used these things. What? I can't use styrofoam, right? Because if I use styrofoam for this, it would never hold the books up. The books would would move and fall, right? Because why? Well, this is always heavy. It's a heavy. It's usually a rock, might be steel, something like that. Something that's very heavy. Why does it have to be heavy? Because we have to generate friction at the base of this. If there's no friction there, then these books are simply going to push that bookend, out of the way. So the way to get the friction is what? We know that for friction, we know that F equals mu times N, and the N is what? N is the weight of the bookend. So this weight, that's got to be heavy because we have to generate a large F. And so that has to be heavy. And as a result, because this has to be heavy, it could be called, if we had such a word, this is called a gravity bookend. Gravity bookend because it's heavy. It needs the weight in order to prevent sliding of the bookend. And so this type of wall, we call it a gravity wall, a big, heavy wall that we build for the purpose of holding back our soil, is called a gravity wall. We have to have it heavy, so, we need to generate friction at that base. That's one of the things we need. Now, the other thing about this bookend is notice its shape. It's deliberately, trapezoidal because we want a wide base. Why do we want a wide base? Well, let's think about it. So why is this bookend, if I took a bookend and I put a very heavy steel bookend, but it's shaped like that, why doesn't that work? Well, even though it's really heavy and we can generate good friction at the base, what's going to happen? Another mode of failure is overturning. This is going to turn over. and it's going to pivot about this point, in this case on the right corner, right bottom corner. And so we need two things from this bookend. It's got to be heavy, and it's got to have a wide base so that it doesn't overturn. So heavy to resist sliding, a wide base to resist overturning. And in this case, now what happens? Well, when I look at this, I'm looking at a pivot about, again, now I have the point at the lower right-hand corner of it. And what we do, well, this is how we analyze this. For instance, let's just take this rectangular one here. If I'm worried about overturning, I take moments about this point here, the lower right-hand corner, and what are my, as this thing starts to rotate, there's liftoff of the base, and I just have my force from my books. I have my weight from my weight of my bookend, and I'm taking moments, so then I'm taking moments of those forces about A. Well, what's my moment arm? If my moment arm from, in other words, well, I'll put it this way. I need to have my counterclockwise moment be greater than my clockwise moment in order to make sure it doesn't overturn. And what happens is if I have a really narrow base, then my moment arm is really small. So I need a wide base with the idea that I make my moment arm much larger, and so I can generate the moment, the resisting moment due to the weight. I get a much greater moment, resisting moment, due to the, caused by the weight, because I have a much greater moment arm. So, so I need that wide base to prevent overturning. I need this wide base to prevent overturning. And then, of course, I need the weight. The way to analyze it for friction, sliding, is that I have my normal force, which in this case is equal to the weight. You can see it's in equilibrium there. And I have to have that my coefficient of friction times my normal force is greater than my force from my books or my soil. So I can analyze this for both sliding, this is sliding, and overturning, two different analyses. I'll make one other comment. You are probably familiar with another type of bookend that, basically has this shape. It has a T. Now, how do we analyze that one? Well, notice those types of bookends, in other words, these kinds of bookends, are not heavy. They're light. So how do they work? Well, what you have to do with these kinds of bookends is that you have to put books on that part of the bookend, and the end result is that these books now become, the books that are sitting on top of the bookend, in a sense, become a part of our bookend. They give us the weight. And if you notice that these always have these sorts of, bookends, they're not shaped like that. They're not shaped like a backward L. They always have an extended base. Why do they have that? Because to get overturning, you're going to pivot about this point. And what does that do? That increases our moment arm to prevent overturning. So the weight of these books helps prevent sliding, and this extension out here helps prevent overturning by extending our moment arm. And sometimes we will build a wall like this as well. So in other words, we can build a concrete retaining wall, for instance, with this particular shape, and then when we analyze it, and of course this is soil back here, not books. And how do we analyze it? Well, we analyze it and we have to consider the soil that's sitting here. That's basically part of our wall. So that is included. In a sense, we're making this kind of wall into a gravity wall. Although the wall itself is not heavy, we are actually relying on this the soil sitting there to act as part of the wall and give us the gravity action. Okay, so let's just do a simple example here. Suppose I have a concrete wall like this. Now I'm keeping the geometry simple. I'm making it rectangular, and we'll see how that works. I have clay. I have gamma saturated. I have a Ka of 0.5. What is that? We'll see how that plays into this. So I know what the Ka is for that clay. And I'm going to consider both sliding and overturning. I'm going to use a factor of safety of 2.0. At the base of the wall, the coefficient of friction is 0.3. That is between the concrete and the soil. And the concrete unit weight is 26 kilonewtons per cubic meter. We're going to use our expressions that sigma prime is equal to sigma minus u, which means that sigma is equal to sigma prime plus u. So just reversing that, or rearranging that equation. And what we want to do is find the total force and the wall width to prevent overturning. Okay. When I say the total force, I mean the total horizontal force on the wall. And then I'm going to try to find the wall width to prevent overturning. We'll also do something with sliding at the end. Okay. So what do? I do my usual table, and I'm going to add a little bit. So we've already done this. We have depth, sigma v, u, sigma v prime. Now I'm going to add two more columns, sigma h prime and sigma h. So let's see how we get these. So we've already done this a bunch of times. Now we're just going to add two more columns. So let's start with the beginning. So I'm going to consider two depths. My points of interest will be at the ground surface and at the bottom of the wall, 4 meters. So in other words, there's 0, there's 4 meters. So I'm looking at a depth of 4 meters here. At a depth of 0 and 4 meters. Well, at a depth 0, there's no sigma v is 0, u is 0, sigma v prime. We get all zeros here. So the more interesting one is the one at 4 meters. I have saturated clay. I have my water table at the ground surface. So at 4 meters, I'm 4 times 14, 56. There's my 14 for my gamma saturated. My pore pressure, it's below the water table, so 4 times 9.8, there's my point of interest. You can say, okay, drawing my piezometer. Piezometer goes there. So I get 4 times 9.8, 39.2. Sigma v minus u gives me 16.8. Okay, now I put in, so I know how to do this. So the next part is that to get my sigma h prime using my basic definition, that's Ka sigma v prime. Why is it Ka? Because this is the active region. Oh, okay, so in other words, we are assuming that the wall has been built. Once this is built, then what happens? Then this wall moves outward. It's like putting up our bookend and then letting go. The wall moves outward, so I have Ka. I have active pressures. In other words, the wall is moving away from this soil. And that is why I get an active earth pressure there. So I'm given that Ka is 0.5. So this is simply 0.5 times 16.8. I get 8.4. And then to get my sigma h, well, I'm going to use this form of the equation. And sigma h is going to be sigma h prime plus u, sigma h prime plus u. So I simply, my sigma h prime is 8.4, my u is 39.2. I add them together, I get 47.6. Okay, so I'm going to draw the stresses on this wall, the horizontal stresses on my wall. There's my wall right there. It's 0 at the top of the wall, that's the 0. The bottom of the wall is 47.6, and it's linear in between. You can do the calculations, but it's all linear in between. So what do I have for my stress distribution on the wall? It looks like this. It's a triangle. And I need to convert that stress into a force to do my analysis. I can't do my analyses with stresses. I have to use forces. So how do I convert the stress to the force? Well, if you remember from your statics, I find the volume, quote, the volume of the stress block is the force. Now, I'm going to take 1 meter perpendicular to the paper here. And so my volume is what? It's the area of the stress block times the width of it. So this is a triangle. So it's 1/2 the base times the height. That's the area of the triangle. I'm taking 1 meter perpendicular to the paper, so I multiply by 1 meter. So the volume of my stress block is 1/2 the base. There's my base of my triangle. The height is that, it's 4 meters, and then 1 meter perpendicular to the paper. You can check the unit. The units all work out, they cancel, and I get 95.2 kilonewtons. So now I'm going to analyze overturning, and I'm worried about rotation, about the lower right corner in this case. I'm using a rectangle, so just to keep the geometry simple. It's not the best design, but I don't want to make this difficult with geometry and things. So just to keep it simple, I have the weight of my wall. I have my 95.2. And then it's a triangle, so that 95.2 is 1/3 up from the base. As you know, the centroid of the triangle is 1/3, using the 1/3, 2/3 rule. So I know all the dimensions. Now, my W, I don't know what the W is yet. I know I'm going to call this width B. So my weight is what? It's going to be the volume of this concrete times the density of concrete. And again, I'm taking 1 meter perpendicular to the paper. So my weight is going to be 4 meters times B. That gives me the area of that rectangle times 1 meter perpendicular. So I have 4B times 1 meter. That gives me the volume of the concrete times the density of the concrete that was given. And I get that the weight of my wall is 104 times B. We don't know what B is yet. Now, the way that we define factor of safety, and this is just a definition, is the resisting moment divided by the overturning moment. Well, what is the resisting moment is this W times the B over 2. Because that resists the overturning. So in other words, that gives the counterclockwise rotation, that W times B over 2. The overturning moment is the 95.2 times the 1.33. So that's the clockwise moment. So I'm taking the resisting moment over the overturning moment, and in this problem we specified, we required that the factor of safety be 2. So I get the resisting moment of 104B, that's the weight, times the moment arm, B over 2. And then in the denominator we have 95.2 times 1.33, and we're saying that we require 2. I solve for B, I get B is equal to 2.2 meters. So based on overturning, we need 2.2 meters width of wall. Let's look at sliding. Sliding, we have a slightly different free body diagram. Note, why do we have a different free body diagram? Because for overturning, we assume that we're pivoting about this point, and the wall is only touching at that point, which means we have a force here and a force there, but they both go through point A, so I don't need to know what those forces are. So, in other words, there's liftoff at the base, and that liftoff means that there's no contact with the soil, so I don't have any forces at the base, I just have forces at the lower right-hand corner once liftoff begins. On the other hand, for sliding, I have an N and a mu times N in addition to my W and my F. So it's a different free body diagram that we're going to analyze now. And if I look at my free body diagram, take the sum of the forces in the y direction equals 0, I see that the wall is not moving in the vertical direction, so N is equal to W. And my factor of safety in sliding is defined by the sliding resistance divided by the sliding force. What is the sliding resistance? Well, my sliding resistance is this mu times N, and the sliding force is my F. We've already figured out what the F is. My coefficient of friction is 0.3. So N is equal to W, so 0.3 N is equal to 0.3 times W. We've already figured out the sliding force is 95.2. We can see it from up here. And this has got to be equal to, and then again my W is 104B. So, and that's got to be equal to 2. I solve for B, and I get B is equal to 6.1 meters. Now notice it's not the same as the 2.2. I have to have a factor of safety of 2 for both conditions, so I have to, this is my answer here, I need to build this as 6.1 meters. It's a huge wall, and this is one of the reasons we don't build a wall like this. I'm using this as an example, and this is an example showing you how huge a wall needs to be to resist these forces if you're just going to build a simple gravity wall like this. So, okay, I'm going to stop there. So we find, well, then that end result is that we find other ways. It's too expensive to build a huge concrete wall like that. And we find other ways to create a large mass. For instance, sometimes sometimes if it's convenient, you can just use huge boulders to create a huge mass. Other ways, we'll talk about other ways that we can use to build a huge, heavy wall.